Hello, my name is Manuel Rubio Sanchez. I'm a professor at Universidad Rey Juan Carlos in Madrid, Spain, and I'm going to present our work on optimal axis for data value estimation in star coordinates and radial axis plots. So radial axis plots are projection methods that map high-dimensional data onto a lower dimensional space, which is normally a plane. So data samples are represented by points or dots, and it is also possible to include information about variables by showing a set of axis vectors where each one is associated with a variable. It is also possible to include axis lines that allow users to estimate original data values by projecting points orthogonally onto these axes. So for example, in the image on the right, we have a data set of cars, and we can estimate the value of horsepower for the car represented by the red dot by projecting it onto the axis. So in this case, we would guess, or we would estimate that the value of horsepower for that car is about 150. So the whole paper revolves around this idea of estimating data values optimally. And we're going to show how to label the axis optimally, how to choose alternative axes that allow users to estimate values more accurately. We're also going to provide guidelines for choosing axis vectors and therefore visualizations, whether we would like to update an axis vector or add new axis vectors into the plot. Now the paper is very specific. It's mainly intended for experts in radial axis methods, and it's halfway between a theory paper and a technique paper. So we also provide several theoretical results, and all the proofs and derivations are in the supplemental material. Before we begin, let's take a look at the several radial axis methods that we analyze in the paper. The first one is star coordinates, which creates a linear mapping from your n-dimensional data space onto the plane. The axis vectors are simply the components of the transformation matrix, and the points are linear combinations of the axis vectors, where the coefficients of the linear combinations are the attribute values of the data samples. In star coordinates, the vectors indicate directions in which variables increase, and I've written this in quotes because we're going to see that in fact there are better directions. The length of the axis vectors indicates the importance of a variable, and it's important to note that this is an interactive technique, so users can select the axis vectors interactively in order to accomplish certain tasks. For example, in the image on the right, we've selected the vectors in order to plot data with high values of horsepower and acceleration, but low values of miles per gallon at the top of the graph. Lastly, in the bottom, you have the notation that we're going to use throughout the slides. Orthographic star coordinates is a variant of star coordinates where the transformation matrix is orthogonal. In the context of this paper, it's important because if you add axis lines to orthographic star coordinates, the estimates are going to be more accurate than if you just add lines to star coordinates. Also, it's important to note that we're going to consider that we obtain a particular configuration of vectors for OSC by orthogonalizing some other configuration of axis vectors in SC. So this implies that the columns of V and V orthogonal are going to span the same subspace. Principal component biplots are generalizations of the well-known PCA plot. In biplots, the estimates are dot products between the points and the axis vectors. And these points and axis vectors are obtained by minimizing that optimization problem, where the goal consists of reducing the discrepancy between the estimates and a centered version of your data. Now, because the problem finds the points and the vectors simultaneously, it's going to provide the best possible plot regarding estimation accuracy. So it's going to provide a lower bound for the total estimation error across an entire data set. Adaptable radial axis is a hybrid approach between star coordinates and principal component biplots. In this case, users can select arbitrary axis vectors, so it's an interactive technique, and the points are plotted in order to maximize the estimation accuracy for a fixed set of axis vectors. The optimization problem in this case is identical to the one for biplots, but only the points are the variables. So here you have the solution, and it's worth mentioning that the estimates for this technique are identical to the estimates for OSC. So having seen the diverse radial axis methods, the first section of the paper introduces how to optimally label the axis, or in other words, how to optimally calibrate the axis. Now this sounds obvious, that you would have to perform this operation, but you have to be careful because you can't just apply the calibration approach in biplots to your method, because it might give you very incorrect estimates. So for example, in this case, we've used a data set of cars, and the values for displacement, the displacement variable are between 68 and 455. So if you notice on the image on the left, if we project the points orthogonally onto the axis, most of the values are going to be less than 68, which would be false. So ideally, we would like these points to lie within the gray region. And if you scale the axis and shift it appropriately, well, we see that the labels appear in other locations, and now most of the points lie within the gray region. So you can use line axis within any dimensionality reduction method, but you have to be aware that you have to label the axis correctly. We accomplish this by solving that optimization problem. The alphas would be the scalings of the axis, the betas would be the shifts, those dot products would be the estimates, and finally x would be the data values. So these are the optimal solutions. They are pretty straightforward, but you can find the full derivations in the supplemental material. And finally, the final formula indicates where you would have to place a particular label. Even though the previous calibration approach enhances the estimates considerably, it's possible to find different directions, different axes, that lead to even an increased accuracy when estimating data values. So for example, in the image in the left, we can assume that the values for displacement increase from left to right. But actually, a better direction is this oblique new direction in the right at about negative 20 degrees. So we propose using these new alternative axes, and we've analyzed them in great depth in the paper. This is the optimization problem. Again, we have the estimates, shift parameter, and the data. And in this case, we don't need a scaling parameter because it's already embedded in V, since V is the variable of the problem. So these are the solutions, and again, you can find the details in the supplemental material. It's interesting to analyze the angle differences between the original and optimized vectors. In general, these differences will be small, as we can see in the example, and also from these distributions that we've obtained through a couple of simulations that we've done. And the angle differences are usually less than 60 degrees, but some can be larger. And in these cases, this is a clear indication that the original choice of axis vector is probably poor. So users should really think about the original axis vector and consider updating it maybe to a direction that is more similar to the optimized vector. In general, we would like the optimized vectors to be as similar as possible to the vectors that we're using in our radial axis method. And we've seen that the optimized vectors are similar to the ARA vectors, but not to the star coordinates vectors. In fact, there seems to be an inverse relationship between the lengths of the star coordinates vectors and the lengths of the optimized vectors. But there should be some middle ground. So we also propose to scale the axis vectors of star coordinates so that they will be as similar as possible in a least square sense to the optimized vectors. And this scaling parameter can be found by solving this optimization problem. And well, the solution is expressed in this nice closed form formula. And again, the details are in the supplemental material. We have also analyzed the information provided by the lengths of the optimized axis vectors. So initially, we thought that the larger vectors would indicate better estimates because this is exactly what happens in ARA plots. So as you stretch a vector in ARA, the labels get squashed together, and this means that the method is going to focus on representing those points or represent the values for the variable better. So we assume that this would happen also when using these optimized vectors, and in fact our initial results seem to suggest that, but we were using standardized data where the variables have the same variance. And it turns out that this only happens if the variables share the same variance. If not, then the lengths of the optimized axis vectors are more correlated with the variance of the variables. So this is clearly an unexpected result worth mentioning. In this slide, we show a comparison of estimation error for the three methods. And when we apply the calibration approach, well, the estimates are enhanced, obviously. And, well, you have the same accuracy for ARA as for OSC. And the estimates for star coordinates are not as good because, well, as expected, because the estimates for SC are poorer than for ARA and OSC in the first place. So this was expected, but what was not expected is that if you apply the optimal axis, then the accuracy for the three methods is the same. So this is pretty curious. Note that the points and axis vectors in all the three cases are different. And also, what this indicates is that it doesn't matter which method you use as your starting point. You might as well just use plain star coordinates, and then if you apply the optimized axis, you're going to achieve the same accuracy as if you had started with ARA or OSC. So now we're going to see how we can incorporate the optimized vectors in other methods, and in particular in Radvis. Here we've calculated the vectors and located them at the anchor points of a Radvis plot. The dataset is the Olives dataset that is well known. And what we can see is that the vectors ideally should point in not towards the center, but in the opposite direction, as for example this vector. Some vectors don't point exactly in that direction, and this is the most interesting vector here because it points inwards. And this is very strange because the values of a variable should increase in the direction of the anchor points, but they seem to increase in the opposite direction. So this clearly indicates that the ordering of the variables here in the Radvis plot is poor. The polymetallaic variable should be probably placed somewhere around this zone. So we've done that, and we've swapped the palmitoleic variable with the palmitic one, and now we have a better ordering of the variables around the Radial circle. And nevertheless, you can consider these directions when, for example, trying to see which values, which points have the greater values for a particular variable. Now, if we didn't color the points in any way, we would assume that the points with larger palmitoleic values are these ones over here, because these are the points that are closest to the anchor. But in fact, that's not the case. And now if we visualize the vector, this red vector is the same as this one, but just scaled and located here in the center. Well, we see that, in fact, the variables increase in this diagonal direction. So, in fact, now we can see that, in fact, we could have the greater values either in this zone or in this zone, and in this case, they are in this region. A drawback of the previous optimal axes is that they lead to inconsistent models. They are inconsistent because the projected points are the same, but we're using different vectors. So now our new goal is going to be to update or add one axis vector while the main remain fixed, and we want to maximize the estimation accuracy, but with a plot that is consistent with the model, with the star coordinates or ARA. So in the first approach, the user is going to define an orientation, and subsequently the method is going to find an optimal direction and an optimal length for the vector. In this case, we're adding a new variable into the visualization. Naturally, the user could select multiple orientations. So we propose drawing a colored curve on the plot to indicate the optimal length of a vector in any orientation. In this case, the color corresponds to the estimation error, and we can see that the best values are obtained here in the fourth quadrant. This is the optimization problem that we'd have to solve. V sub n is the new vector in a particular direction. Lambda is just a scalar that can be positive or negative. And the solution for star coordinates is the minimum of a fourth degree polynomial. So you basically have to compute the roots of a cubic polynomial, which can be done without any problem. And for ARA, the objective function is a quotient of polynomials. So the function is much more complex, and we use a direct search method to find the solution. The optimal vector that leads to a consistent model over any orientation can be obtained by solving this optimization problem. In this case, v sub n is the variable. And for star coordinates, we use a gradient descent method, while for ARA, the function is more complex, and we use a recursive search approach. So to recap, we've shown how to label axes optimally, that is, how to calibrate them. We've also proposed using alternative axes for enhanced data value estimation. We've proposed a strategy for updating or adding vectors that leads to consistent models. We've provided guidelines for choosing axis vectors, and in particular for identifying poor initial directions. And we've also mentioned several theoretical results, and you can find the proofs and derivations in the supplemental material. Thank you very much for your attention.